All right. So the last time we ended talking about the APY, right? The annual percent yield. And if you remember, the annual percent yield is basically the amount as a percent that you get when you compound interest on like monthly or weekly or even daily basis, right? So, like in this example that we ended with, we had an account compounded daily at 6.5%. And the APY is how much you're getting after that time. Here's the thing. So APY stands for annual, that being the imperative word, percent yield. And every time I do the APY, I forget that it's annual. So in these examples, I wrote them correctly on my initial notes. Because you remember, I didn't put how many years, and I added for 3 years in the moment. And the reason I didn't have how many years is because the annual percent yield is the annual. It's for 1 year. So all of this should be 1 year. All right, so it's going to be a little different for this, the one we ended with on Tuesday. And I do apologize. As I said, I think I've mentioned this when we started this unit. I almost know nothing about finances themselves. I can do the math, obviously, but if you ask me like to define strictly what an annuity is, I couldn't really tell you in terms of, non-math related things. Anyway, let's see what this one is. And then to the 365. And then we get that, and then -1, and then times 100. So it should be, again, I apologize, 0.067, we'll round. And then as a percent, it's 6.72%. Right? And that makes a little more sense. Now, what we did find was still meaningful data. So that 21.5% that we found, that is still meaningful, but you have to interpret it in a different way. So that 21.5% wouldn't be the annual percent yield. It would be the percent yield over 3 years, if that makes sense. But whenever you do the annual, it's just 1 year. There you go. All right. So let's do this last example because I kind of like that, and then we'll kind of keep going from there. All right. So, and just feel free to yell at me if you have any questions about anything. I haven't put any new homework up yet. I figure once I get the test back, I'll put new homework up. I don't want to overload anyone. But let's do this. So this example here is kind of cool, I think. And just let me autofocus. Is that better? Oh, there we go. So you have the option of 3 different banks to invest your money, which that could happen. Bank A, you can invest 7% compounded biannually. Bank B compounds at 6.89% monthly. And Bank C compounds at 6.5% daily. I don't know what kind of bank compounds daily, but all right. Which bank will give you the greatest yield? And as I said, maybe in this situation, for some reason, you are interested in how much money you'll have over like 5 years, right? And if that was your interest, what you could do is you could do the percent yield over 5 years. But for me, I'm just going to do the APY because that it really is. I feel like you'll run across that more often. You're not going to find like percent yield over some number of years as much. You'll find APY. It's so common it has an acronym. So I'm going to compute the APY for each 3 and see what it is. The biggest one is the best because that will give me more money. So let me do A. And this gives me an opportunity to recall what the APY formula is. So APY, it's going to be 1 plus R over N to the no T. T is 1, as I said. So it's just N minus 1. Okay. So again, I apologize, but up here when we did this on Tuesday, I put T in there. T should just be 1 because it's annual. All right. And so now you just plug in all the relevant information. So for A, for instance, my R is 7%. So it's going to be 1 plus 0.07. And then N it's biannually. So that's N is 2. And then it's just 2. And then minus 1. So let's see what we get. 0.07 divided by 2. So 3.5%. Plus 1. And then you square it. to get that. And then you subtract 1 to get that. And so as a decimal, 0.071225. You can be as precise as you like. In these APY cases, like here, let me just finish writing it. So it's 7.1225%. For these APY problems a lot, if I were to round this to 0.07, then you wouldn't see any difference, right? Because the interest itself is 0.07, it's 7%. So for these ones, you probably don't want to round too much. It depends on the problem. You know, if you have a huge APY compared to your APR, your annual percent yield, then you can round probably a little easier just because there's more difference. But here, we do want to see the difference as much as we can. And so rounding will eliminate some of that difference. And so you probably don't want to do it. Anyway, so we have just over 7% for A. For B, we have 3 banks, right? Yep. So for here, let's see what we got. APY. So again, same formula. So I have 1 plus. For B now, I come out at 6.89. So that's 0.0689 over, and it's monthly, so that's 12 for N. 12, all to the 12th. Right, and let's see. Let's see if I put it. Sometimes it's hard to see where this calculator goes, and I can't fit everything in. There we go, perfect. All right, so 0.0689 divided by 12. All right, plus 1. All right, to the 12th. Minus 1. Oh, crap, minus 1. There we go. Minus 1. So it's as a decimal, 0.0. And again, I'll just leave it. It's not too much to write, so I'll write the whole thing. 0.7111799. And as a percent times 100, we get 7.111799901%. I don't know where the 1 came from. It's a little weird. That is kind of odd. All right. Anyway, so it's less than Bank A in any case. Yeah. All right, and we'll just do the last one, C. And so again, same formula, APY. So 1 plus, my rate here is 6.5%. So 0.065. And now we're daily, 365. All right. And so you put the 365 in the exponent too. Minus 1. All right, let me see. Cool. Alrighty. And now we just compute some more stuff, right? So this is the last one here. So 1 plus, oh, well, I'll do it the same way. 0.065 divided by 365. All right, it's very tiny. Plus 1. And now this is where it will kind of blow up to the 365. And minus 1. Blow up maybe is a loose word. Times 100. Right, so as a decimal, it's 0.0. I'm not going to write all this out because this one doesn't really matter. 1.5 maybe. And then it's 6.715%. All right. Oh, there we go. So obviously the best one is going to be Bank A, right? Bank A and Banks B aren't really that far off. I'm what, 100th% off? It's really nothing at all. So either of those would be fine. Bank A would probably be, it's obviously the better one. Bank C, you probably just want to avoid Bank C, right? Because you're getting, you know, almost half a decimal point off, perhaps, yeah, percentage point less. So, yeah. Any questions with those? And again, you could do, like if you were interested in a 3 or 4 or 5 year period or whatever, you could compute the APY for those years and you'd get something, some percentage, right? And it's just telling you how much money you'll get as a percent of your principal. Right? Your principal cancels out, you'll notice, so it doesn't really matter, but yeah. Any questions? Cool. I think that was it for these. Oh yeah, and then continuously compounding. I forgot about it. All right. So and this is the last topic on those notes from the other day, on Tuesday. And this is actually kind of interesting. As I said, we won't get into it too much, but so recall that N is the number of times we compound. So if N is 12, we compound monthly. If N is 365, we do it daily. And all that compound means is that you compute the interest on your money in your account. So like if the interest is 4.3%, you take the interest of 4.3% interest and you add it back in. All right. So you do that N many times. And what's interesting, as we kind of saw in some earlier problems, is when you increase the number of times you compound, you generally get more money. If you do it monthly, you get some money. You get more money than if you do it yearly. If you do it weekly, you get more money than if you did it monthly. And the more times you do it, the more you'll get. Now, it is just a slight difference we noticed, right? We did a couple examples comparing and contrasting different numbers of compounds on an account with like the same principal, but you still do get a little more. And so the question is, what happens as n goes to infinity, right? Like what happens as you do infinitely many compoundings on some principle? You might expect it to kind of blow up, right? You might expect it to make you have infinite money, essentially. But that's not what happens. So what happens is very bizarre. What we get is this, and I'll write the formula here, but what we get is this letter E kind of pops out. So let me give you the expression or the equation, and then we'll talk about it. So it's P naught, which is my principal, times E to the RT, right? Where R is my rate, interest rate, and then T is time. And E is this thing called Euler's number. And if you might have ran across it before, I don't know if they teach it in high school. They probably do. They must. I remember learning about it. So it's kind of like pi. So like in the same sense that pi doesn't repeat and it can't be expressed as a fraction, this is the same kind of deal. It's approximately 2.718 whatever. And it even, most calculators have a button for it. So like this one here has one right. It's hard to see, but it's right next to the up there, E. I think that's it. Yeah. Sometimes they have separate buttons, but pi is there, E is there. And if you put it in, you should get E. There we go. So it does work. And again, just like pi, if you did pi, you get pi. So just it's a constant. And so what happens is, let me get another sheet of paper. It's kind of bizarre. What happens is, so remember the other formula we had, right? So we had A equals P naught 1 plus R over N to the NT, right? So this was our interest for compounding, and this is our formula for compounding interest, compounded N times at a rate R with principal P naught, right? And all it's doing is you're iteratively, there's the word, adding R over N percent to my P naught principal. And you're doing it over and over again, N times T times. And so what happens is that as N goes to infinity, and whenever you say things like N goes to infinity, it instantly sort of evokes like a calculus sort of thing. And if you take pre-calc or calculus and you do things with limits, you can actually see where this all comes from. But basically, as you compound more and more, this formula gets really, really close to this formula, where E, as I said, is that constant 2.718, yada, yada. It's really weird. It's kind of bizarre. But yeah, so if I compounded 1 million times a year, if I put N equals 1 million in here, and I found out how much was my account like after a year for some principal, and then I plugged my principal into here and put T equals 1, again, at a similar rate, you would find that they're kind of close. And as N goes to infinity, you're going to get really close. It's just, as I said, very bizarre. It's a very bizarre phenomenon. But I guess the point is that it's just because the whole reason I'm talking about this at all really is just to answer the potential question of, can I compound more and more to get more money? And the answer is no. You hit a ceiling, and then it kind of stays the same. And this is kind of the ceiling, essentially. Like this function is essentially your ceiling. Which is sad and interesting. Anyway, we call this situation continuously compounding interest. Right, so the continuously there is kind of the E in some sense. Like the reason it's called continuously is that every second of every day, every microsecond of every day, the interest is being computed and put back in your account. It's not even more than that. And that's why it's called continuous. Like the reason it's called continuous is that like if you took the time, like pretend this is like time, and you kind of put down oh, this is each of these little ticks maybe is where the money's compounding, right? It's called continuous because there wouldn't be a gap. Like there'd be a tick there, and then there'd be a tick between those ticks, and between those small ticks, there'd be another tick where it would compound, and like it's compounding all the time. Like there's no break, there's no gaps where it compounds. So that's where the continuous comes from. Again, continuous does have a definition that's more precise in calculus. We won't get to it. But yeah, it's really neat. We'll just do one example. I don't think we'll really talk. It won't be really relevant to anything else we do. So we'll just do one, just kind of play around with it. Suppose an account compounds continuously with an APR of 1.59%. How much is in the account in 5 years? All right, and then let's compare this to the value in the account if it is compounded annually. So let's see. So if I have 1.5%, 1.59, so A equals, and I didn't give a P naught. So let's say P naught, let's just say P naught's $100. So $100, and then we'll do it continuously. So E and then 1.59, so that's 0.0159, and then for 5 years. All right. So again, I don't know how exactly they'll match here, just because if we're doing it annually, it's gonna be very different, but we'll see what happens. Anyway, so let's see what we get. I'll plug it on my calculator. And just like I said, when you're using E, in case you do run across E later on in your life somewhere, treat it like pi. So I'll do 0.0159 times 5. Oops, sorry about that. 0.0159 times 5. So I get something like that. And then I'm going to do second E to the second answer. There you go. So I get one, whatever that is. And then times 100. So that is my answer for the continuously compounded one. And I'll round it to the nearest cent. So 108.27. Okay. And yeah, I don't know, it will definitely be much less if we do it annually, right? Like annually. So this is continuously. This is annually. So annually, it's gonna be significantly less, right? Because annually, and just compounded once, like once a year. So you're adding just 1.59% on, which is a very small amount. So it's just 100. So it's like, so it's a 100, and then 1 plus 0.0159 over 1 to the 1. It's very, very small. So 100 times 1.0159. And you probably could have guessed 101.59. So the big difference there. Usually too, and again, it will depend on the situation, but usually if you're doing these kind of problems, they will tell you like at a continuous interest rate or something like that. Usually, I don't know if they usually call it APR. As I said, the financial side of things, not my jam. But I know that oftentimes they'll say it's continuous interest rate or something to that effect, to note that it's doing it continuously compounding. What's also interesting, and again, we're not getting into this because it requires logs, but what's also really cool is if you have any other compounding form, any other compounding account, right? So suppose you have an account that compounds monthly. What you can do is, and it compounds monthly at some rate, right? What you can do that's kind of neat is you can rewrite your compounding formula into this form. Now your rate will be different, but you can take any formula that you have for a bank account compounding sometimes, or at some rate, some annual rate like N, and you can rewrite it in terms of a continuously compounding model, which is kind of an odd thing to do, but you can do that too, and the interest rate will change and stuff like that. So for instance, in this case down here, we could rewrite this a model for this bank account in this form with a different little r rate. It'd be the continuous interest rate. Besides the point. All right. So again, that's just kind of a neat little aside of what if you do take more math courses and more financial courses or things like that, it's more things you can look into that are kind of fun. But we are done with that. So let's keep going on, because we only have 4 whole weeks left, which is mildly scary. And let's see. So I put these up last night. These are the next notes. I don't know. Let's see. I thought that we would do some review, but I already kind of did some review. So maybe we'll skip the first. So this problem here, you feel free to do these problems too if you need to review. This is just find the value of the interest at the end of 10 years if the account earns interest in 2 different ways. So this is compounded annually. So it's n equals 1. This is simple interest. So that's, you just get it once. If you're already doing this, I would do this not annually, maybe like monthly. Otherwise you'll get the same answer. And then this one here is an APY example, which I already did. We already talked about that a little bit, so I don't want to drag on too much with APYs, but it's another one you can do. It's kind of a good problem too, because you're calculating the APY for an account that pays 15%. 3 different ways. If it's compounded daily, monthly, or annually. So you can really see how the APY changes as you go. Right? We'll come back to it if we have time. I want to make sure we cover everything, and I don't want take your time too much. So 6.1. Yeah, so chapter 5 was really just about compound interest, and the APY and like simple interest we did too. So just kind of basic kinds of interest. But now we're kind of moving to some more interesting topics. Annuities, as I said, annuities are kind of weird. And I don't know what the proper definition of annuity is, like, financially. For us, it's basically going to be just a savings account that we do things with. So, and that might be the definition. Anyway, so we're gonna start with an example, and then we're gonna kind of segue. So, so this example, you have an account with $0. So we're starting with nothing in our bank account, and you get an APR of 12% compounded monthly. Every month, you deposit $100 in the account. How much does the account have in it at 6 months? And let me, just a second, here's my notes. All right, I just need to make sure I have these handy. All right, there we go. So we're gonna make a little table. So this is one of those examples where we just make a table and see what happens. So I want 6 months, and I want the account information. So I'm gonna have month, the balance in my account, end of month balance. Yeah, I'm gonna say interest, and then end of month balance. So this problem's a little complicated, right? So, and then we have 6 months. 0, 1, 2, 3, 4, 5, and 6 if he fits down there. All right, so this is the beginning of the month. I have $0, right? Nothing in my account. And consequently, I get 0 interest. Make sense? Makes sense. But at the end of every month, I put $100 in. All right, so at the end of the month, I have $100 because I put the $100 in the account. All right, so month 1, I have $100, right? And so the interest is computed on the amount in the account at the beginning of the month. So my calculator's over here. And so, I mean, we can probably, I guess we really can't, no, we could probably do it, but we'll do it in a calculator. So 12% of 100, I guess that's not that bad, 0.12, so it's $12, right? So my interest is $12, and I guess I should have dollar signs. All right, and so I get 112, and don't forget, I have my, what is that? I have my, wait a second. Oh, I'm so sorry. I forgot. I did this last semester too. I made note of it. It's compounded monthly. My APR is 12%. I always forget this. So when you're doing your interest, it's 1%. 12% over 1 equals, or 12 equals 1% monthly. I always forget that APR is a tricky thing because that's how much interest you get over the entire year. And so if you're doing things monthly like we are, it's not 12%, it's 1%. My interest is $1. 1% of 100 is $1. Anyway, so now my balance is 101, And then I have the $100 that I threw in there at the end of the month. So at the end, I got 201 bucks, 201, right? All right, that looks good. Next on the right track. Any questions so far? All right, so now we just kind of repeat. So at the beginning of this month now, I have 201. My interest on that is 1% of 201. So 0.01 is $2.01. And then I add it to that. So $2.01. And then I add it to the balance to get, I don't know what, 203.01. And then I add my 100 bucks. So I have 203.01. So we did 201 plus 2.01, the interest, and then plus my 100 bucks that I add. And it's the savings account. So I got 303.01. Cool, that's what I got before. 303.01. All right. So it's a little confusing. And I think it's just confusing, might be confusing because the interest only applies to the beginning of the month balance. It could be different depending on your bank, but all right, let's keep going. We'll finish. 301 or 303.01. I take 1% of it to get 303 rounded in the nearest cent. Add that back in along with your 100 bucks. So I'll do plus 100 plus my initial 303.01. So it's 406 and 4 cents. 406 and 4 cents. All right, that comes down to moving next principal. 406 and 4 cents. And so my interest on that times 0.01. So I get $4.06. I guess we could have figured that out. $4.06. And now I add that to my balance along with my $100 that I deposit. It's like a savings plan. It's like every month you would be adding in $100. Say you're trying to save for X, Y, or Z. So 5, 10, and 10 cents. All right, and just a couple more. And I thought the most interesting thing, but it doesn't get it gets kind of better as you keep going. As you get in the habit of, or the pattern. 5, 10, and 10, so at 10% or 1% of that. $5.10. Oops, sorry about that. $5.10. 5, 10. Now I add it. Plus 100 plus 5, 10, and 10 cents. 6, 15, 20. And just the last one now. Oh, well, I guess this is after 6 months. It's never clear to me. I'll just do the last row. All right, times 0.01. So 615. And then plus 615, 20 plus 100. 721 and 35. 721 and 35. All right. So there we go. So at the end of 6 months, we have $700.21 and 35. $721.35. There we go. And so we deposit. How much money do we actually put in the account, right? We put in 100, 200, 300, 400, 500, 600, $700 overall, right? And so this is at the end. At end of 6 months. So that's why you have 700 and not 600. If you look at the beginning, we put $600 in. So the interest that we generated was about 15 bucks. So and you'll note too that the interest does go up quite a bit because you keep adding in $100. And so that kind of blows it up more than it would if it was just normal interest. Anyway, so this whole situation can be expressed with an equation. And I will say it's not the prettiest thing on the planet. I always mess it up, but let me write it down and we'll talk about it. So it's payment APR over N. Don't want to misspell anything here. And then 1 plus APR over N to the NY minus 1. It's a weird, funky formula. All right. So let's kind of, let me describe things to you. So PMT here is the payment. So PMT equals the amount of regular payment. All right, so like in the example we just did, it's $100. That's how much you're regularly putting into the account. And this formula too is assuming that your account starts at 0. So if, for instance, you have an account with $1,000 in it initially, it's not going to quite work. I guess you could just add 1,000 at the end probably, and you'd be fine. Maybe, not sure about that. You might have to, don't do that. I don't think that works. I don't think about it more. Anyway, and then N is the number of payments per year. And so, again, this is a very special formula. Like it's very specialized to a certain situation. So at P is the amount of regular payments. They have to be regular. They have to be the same amount. N is the number of payments per year. And what's special here is that we assume that it's also the number of compoundings per year. It must be same as number of compoundings per year. All right, so it's not my favorite equation, largely because of all these restrictions on it. Like we're assuming that the money is put in and it's compounded at the same rate. So for instance, if you wanted to have an account that you deposited money into weekly, you wouldn't be able to use this formula, or you know, because usually money is done monthly, compounded monthly. So if you deposited money weekly, it wouldn't work quite. You would have to change how much your payments were to convert it to basically monthly payments, and then you could use it. It's just a little funky. I wish it was a little more flexible, I guess. But yeah, so there we are. And it's just ugly. I don't like it. I'm not a huge fan. We'll try some examples though, because you can do some fun things with it. The first thing we should do, make sure my numbers are right here. Let's double check. So, oh, and I should note, Y is time in years. So time. Years. All right, same as the other formulas that we've been using T. So let me rewrite it, and then let me use a white sheet of paper too. I feel like the lines don't show up as well. There we go. So we wrote down this PMT, and then I got this ugliness, APR over N, and then 1 plus APR over N to the NY minus 1. Oh, I'm sorry. See, I told you. I need another parenthesis here. There we go. Same for here. There we go. I had too few parentheses. And yeah, so let's see. So in this case, my payment, as we said, was $100. My N was monthly along with my payment frequency. So that was 12. My APR was 12%. And what else do we need? Oh, and Y, we did it for half a year, for 6 months. So Y equals 6. Oh, sorry, 6/12, which is 0.5. We did an example where we talked about how you can have fractional years. It's the same thing. Anyway, so let's try. And I hope it works. I've done this before where I do an example, a long example, and then I try to use the formula, and sometimes it doesn't match, and that's mildly awkward. So we'll see what happens. I don't want that to happen again. So A equals 100 times APY over 12N. So it's 12% over 12, which is just 1%, of course. So I get 1% in the bottom. Yeah. And then I get 1 plus 1%. Not sure what that is. All right. And then N times 12. N is 12. Y is 0.5. All right. So basically there'll be 6 compoundings and then minus 1. Let's see. This is a funky one, isn't it? Let's see what matches. So I'll start with the thing in the middle here. So I get 1.01. Sorry about that. 1.01. Here we go. Is the thing in the parentheses. And then 12 times 0.5 is 6, so it's to the 6th power. So I get that, and then minus 1. And then you divide it by 1%, which is 0.01. Right? And then times 100. Hey, it works. Isn't that exciting? So we get 615 and 20 cents. I always like when things work. 615, 20. And if you remember, that's exactly what we got at the beginning of 6 months. So just be careful with the numbering. If this number would correspond to 7, so that'd be 7 months, that's the same amount you have at the beginning of 7 months. So this formula is going to pop out an answer based on the beginning of the month, what the balance is at the beginning, not at the end. Okay. That's very exciting. I'm glad that worked. All right, and I just want to note a couple things here. The APR, I wrote it as a percent, but remember that percent is decimal. So when you plug that in, it's really 0.01. And the same thing for that one. So, what I did is I had 100 times 0.01 in the bottom, and then I had 1.01 to the 6 minus 1 in the top. And so that's what I evaluated. Do be careful with the percent. So I feel like you might be tempted to say, oh, it's 1%. It's just 1. I could ignore it, but it's not. So to be careful. All right, let's do some more because these are mildly interesting. All right, let's see. This one might be applicable to people. In an effort to buy a house, you begin a savings account, hence the saving plan formula. It's kind of a mouthful. Each month you deposit $200 and the account has an APR of 5%. If you're putting down a down payment of 20% on the house, how much of a house can you afford? All right. And maybe we should set a time limit. I don't know, maybe like in 10 years. We'll say 10 years. That seems like a long time to say, but it's probably a reasonable amount of time to save. So houses are expensive. So put stuff here. No, go there. All right. So let's see. So there's a couple things, right? That's kind of interesting. The first is that you want to put down 20% on the house, right? So that's the first thing you got to figure out. And then the second thing is we got to figure out how much we'll have in 10 years, essentially. And so what we're going to do is we're going to first find out how much we have in the given time. Maybe we'll say 5 years in the given time. And then what we'll do is find out what that number is 20% of. And that will be the most of a house we can buy because that will be assuming we spend all of our money on the down payment, if that makes sense. So let's try it. We'll see if it works. So again, we need the savings plan formula, and I'll write it up here for reference because it is my least favorite formula. APR over N, and then 1 plus APR over N to the NY minus 1. All right, there we go. Keep hearing noises. All right, so again, 5 years, and let's see. So we can kind of plug it all in. So my PMT is 200, the regular payment, and then it's monthly. So we'll assume the APR is compounded monthly too, just because otherwise it won't work. Right, so it's going to be times APR is 5% monthly, so it's 0.05 over 12, and then I have 1 plus 0.05 over 12. N is 12, that's the number of compoundings or monthly payments, or regular payments, I should say. And then the years is 5. All right, so that's what we want to compute. As I said, be a little careful with this formula. I think it's a little tricky, or it can be a little tricky, maybe is a better word. So I'll start with 0.05 divided by 12. Take whatever that is. And then plus 1. And then 12 times 5 is 60. So times 60. That's not what I want. Sorry, let me do that, undo that. I want to raise it to the 60 power. There we go. And then divided. And I want to divide it by 0.05 over 12. So again, be careful when you're doing these things. When you divide by a fraction, I always like to put it in parentheses. So like I did divide and then open parenthesis, and I'll do 0.05 divided by 12, close parenthesis. And that will just make me feel better, even though a calculator might be able to get it without you doing that. Just I always like to err on the side of caution with parentheses. And so that's my number here. And now I just need to multiply by 200. That's a big chunk of change. I didn't know it'd be that much. I don't know why. So, because I guess $200, that's $2,400 every year, 5 years. I don't know. That seems too big, but I guess it's not. Anyway, so it looks like it's 61,601 and 22 cents. Let me just double check my computations. I don't think that sounds right. Let's see, 0.05 divided by 12 plus 1, and then to the 60 power, 12 times 60, 12 times a month. Does everything look good to everyone else? Does anyone see a mistake I'm making? To the 60 power. Oh, I forgot the -1. Duh. I knew there was a mistake. All right. So then -1. I have it up here. I forgot to write down here. I told you this formula is tricky. Be very careful. -1. And now we divide. All right. Okay, I feel better. So 0.05 divided by 12. So it's 68. This whole thing is 68, and now times 20. So much better. It seems too little now. What's happening? Because we're 5 years, so that's...
Shouldn't it be 200, Matt? Instead of 20?
There, thank you. So much better. But thank you. All right, there we go. So 13,601 and 22 cents. That makes a lot more sense. So yeah, always try to fact check yourself. Like you're doing $200 a month and you have 5 years and there's 12 months in every year. So like right off the bat, 12 times 5 times 200. It should be at least 12,000, but it shouldn't be that much more. Like 60,000 is outrageous compared, you know what I mean? Like the interest is never gonna be that much. So there we go. Anyway, so that's good. Now that's how much we have to put a down payment on the house. And if we put all of it in, that will be the most we can afford. So we have to use little percentage stuff, right? So the down payment will be equal to 20% times house cost, right? Now the down payment, if we spend the entire 13 grand and some change on the down payment, that will be the most we can afford, like I said. So I'll put that over here, 13,601 and 22 equals the down payment, which is equal to this. And so to find the house cost, I just divide by 20%. So the house cost, and this is the max house cost, by the way, because we don't have any more money for the down payment, will be 13,601 and 22 over 20.20. And so it's not going to be too much. So it's going to be 13,601.22 divided by 0.2. So it's not the best. It's something though, 68,006.10. So you've got $68,000 at most to spend on a house if you're depositing $200 for 5 years into like a savings account, basically. This is assuming you put down 20%. You know, it depends. Apparently you can do less, you can do more, depending on, you know, how you're doing things, but I think 20% is the average. Any questions? All right. Let's see. So I'm gonna skip this one. Again, feel free to do things I skip, but there's a really fun one I wanted to do. This one on page 5, and this one and the next one are kind of cool. So let's try these. So they're both pretty unrealistic. So your child is born and you decide apparently that you want to build a $100,000 college fund in 18 years. Again, I said very unreasonable. If you get 3% APR, how much do you need to deposit in the account each month to have the desired amount? All right. So what we're going to do is, let me write my formula that I keep screwing up. A equals PMT times 1 plus APR over N to the NY minus 1. over APR over N. All right, so there's our formula. What we want here is we're kind of solving in a backwards way, right? I want to solve for the payment, what it would have to be for me to build $100,000 over 18 years, doing things monthly if I get 3% APR, right? So basically, it's kind of like one of those problems where you're given a bunch of information and you just plug it into the formula and see what you have left to solve for, and then you solve for that. So like, there's 1, 2, 3, 4, 5 variables here, and we're given 4 of them, right? So just plug in everything you know and solve for what you don't, and that generally will work for you. In this case, we want how much do you need to deposit in the account each month to get the desired amount, right? So let's see what happens. So again, I want the total to be 100,000. So I'll plug that in for A. I think we talked about the average cost of tuition, didn't we? I think it wasn't as much as 100,000. It depends where you go, but it can be less, but that's probably a good starting point. That's too much. And so the payment, we don't know. I'll leave that as PMT times, but we know all of this. So basically we'll plug everything in, divide both sides by whatever this is, and solve for PMT. So I get 1 plus the APR I said was 3, so 0.03 done, and it's done monthly. So over 12 to the 12, and then 18 years times 18 minus 1 all over 0.03 divided by 12. Right, so let's see. So as I said, what I'm going to do is I'm going to compute what this ugliness is here, and then I'll get some decimal, and I'll divide both sides by that decimal. So let's just start with that. So there we go. 0.03 divided by 12 plus 1. So that's what the thing in the parentheses is. And then 12 times 18 power minus 1, and then divided by 0.03 divided by 12, again using parentheses. So 285. So what I'll do is I'll do like a little bloop, bloop. So this is about 285 and 94, say. Right. All right, so now, as I said, I'm going to divide both sides to solve for my PMT, my payment, which is what I'll have to use. Right, so PMT equals 100,000 divided by 285.94. There we go. And so let's see what that is. It's going to be so big. 100,000. That's good. Divided by 285.94. So, oh, it's not that big, actually. That's kind of surprising. I mean, it's still a lot of money. I don't think, and most people have that much deposit at the end of every month for, for tuition fund. But we'll say 350, or I guess I'll be more precise, 349. $349.72. Right? And this is for 18 years monthly. So like if you want to see how much money you're just putting in on your own without the interest, you could do times 12 times 18. And so you get $75,540, all right, that you put in just of your own money. and the rest is interest, which is kind of crazy, actually. But I guess that's not bad. What did I get? Yeah, I guess that's what I got before. So it should be good. Let me know if you see any mistakes. Again, this formula is too tricky sometimes. Any questions with that one? All right, and as I said, the next one's kind of cool too. But it's almost reasonable. I guess if they go somewhere else, like if they go to like a state school and they don't dorm, it might be more reasonable. You want to retire in 25 years. The plan, so we've had our children and they've gone to college with our college fund, and now we're trying to retire. And so the plan is to retire in 25 years. The plan is to save enough money in those 25 years so that you can withdraw $50,000 a year and not touch your principal. So basically the idea is that we want to build up enough money in our savings account so that the interest we get every year is $50,000 at least. It could be a little more, I guess. Doesn't really matter. Around 50,000. And that's what I say here. The idea that is you save up enough principal that the interest is at least 50,000. If you get an APR of 7%, how much do you need to deposit every month? Right. So it's kind of a similar idea, but there's an extra step. So as I said, if we want we want $50,000 a year interest, and the interest is 7%. So we're going to kind of do like that house problem, but in reverse. So my interest, $50,000. So we want interest, right? So this will be equal to 0.07, that's 7%, times my principal. Right? So if that's what I want, I need to solve for what my P naught has to be. And that will be how much I have to generate in those 25 years in order to live off my income, my interest, right? So all we do is divide both sides by 0.07. So P naught equals 50,000 divided by 0.07. Right? And so it's gonna be huge, right? So 50,000 by 0.07. That's a big chunk of change. That's a lot of money. So I need to save up $714,285.71. A lot of money. Almost $1 million, right? Three-quarters of a million. If I save that much and I get 7% APR, then I can get $50,000 every year to like live on. It's so much money. Not the $50,000, I guess, is probably average, but this is huge. Anyway, I would feel like I would spend that in retirement instead of living on that. But so what we want to do now is use the interest formula. So I want to use this. So A equals PMT, kind of in the same way we just did it, but now I want to generate that much instead of my kid's tuition fund. APR over N. 1 plus APR over N to the NY minus 1. Okay. So again, so this is how much I need. So that's what I'm going to put for A. That's my desired bank account statement. So isn't that everyone's? 714, 285, 71. And so, again, I want to solve for the payment to see what it's going to be every month for the next 25 years of my life, knowing all the rest of the information. So again, it's monthly. My APR is 7%. So it's 1 plus 0.07 over monthly 12, and then 25 years, 12 times 25, all over 0.07 over 12, right? And much like before, I'm going to compute this ugliness and just divide on both sides to solve for the payment. So 0.07 divided by 12 plus 1 is that. 2, the 12 times 25 is, that's a huge number. I guess that's
Don't forget
good.
the -1 too, Matt.
Oh my God. Thank you. I'm
You're
losing
welcome.
it. I'm losing it today. Yeah. That's really big. I'm kind of surprised. All right, we'll see what happens. So that's huge. Because usually when you have like 1.00 something and you raise it to a power, I mean, it's going to get bigger, but it doesn't usually get that big. But I guess 12 times 25 is pretty decently large. -1, and then divided by 0.07 divided by 12. Think of that. So this is 810.07, give or take. All right, and so now I need to divide my 700 thing by the 810 to solve my payment. So the payment equals, there we go. So let's see. So 714,285.71 divided by 810.07. $881.76. So $881.76. All right, so as I said, this one's like wildly unreasonable. So in order to live on your interest at 7%, and 7% is huge, I feel like, for most non-risky bank account things, you'd have to deposit almost $900 every month for 25 years in order to generate enough money to live on. I mean, $50,000 is a lot of income, but you're still, you have almost $1 million in the bank. So like, I don't know, might as well live on that. But yeah, so it's crazy. This is how much you have to pay every month in order to generate this much, whose interest would then give you that much. And it's kind of neat though, because you could theoretically, if you lived forever, you could live on this. Like you would every year get $50,000 like reliably if this is how much was in your account. So that's kind of the idea in this situation. I don't think most people do this kind of thing. I think most people save this money, they just live on it, like take it out and it will go to zero because presumably you'll die eventually. No one lives forever in this situation. Any questions? All right. So it's just about 5. So we will do some more of this. As I said, when you're doing, I'll post some homework problems on compounding interest next, I think. Probably throw some of these in there too. And as I said, when you're using this formula, I find it very tricky to use sometimes. So just be careful that you don't leave things off or put the wrong thing places. Make sure your APR is a decimal. Make sure you have the -1, like I missed twice. Just be careful because it's just kind of ugly. But yeah, if you have any questions, let me know. Your test should be up this weekend. I'll post more homework next week early. And yeah, anything? Awesome. So have a nice weekend, everyone. As I said, we got 4 weeks left, so we're just about done with the semester. And it should be pretty nice, right? So see ya.